Shelby Nicolau from the Matsker Lab. She'll be talking to us about experimental factors influencing collection of accurate vibrational spectra. Shelby.
Okay, thank you so much, guys, for having me. I'm happy to kind of shift gears for a second and move towards vibrational spectroscopy, and specifically some of the experimental factors that we found to influence collection of accurate vibrational spectra. So vibrational spectra, like infrared and Raman spectroscopy, are most commonly used to elucidate chemical structure. And we're taught from very early on in our chemistry careers, this usually involves assessing characteristic stretching frequencies and intensities associated with certain functional groups. And this typically involves looking for regions where these functionalities are occurring, like CH, carbonyl, or even nitro stretching. And then we build up molecular structure based on the presence or absence of these peaks. But we can also look at how this molecule assembles into solid forms to get more information out of our structure. And this is governed by intermolecular interactions and how those peaks are shifting to influence solid form formation. And two of the main solid forms that we look at using vibrational spectroscopy are polymorphs. So these are crystalline materials that assemble in different forms. And then also multi-component crystals, where we can build new crystal lattices that have two or more components in the crystal structure. And specifically, I have been studying a multi-component crystal where the second molecule is actually inserted as an impurity into the crystal lattice. And this is termed molecular doping. And specifically in this project, we were interested in sensitizing explosives to an impact stimulus by specifically tailoring what that impurity was. And this was done using a molecule known as cyanuric triazide. And one of the ways we actually confirmed molecular doping was occurring was using transmission IR microscopy. And we actually utilized an often overlooked region of the IR spectra, which was the overtone region of our host molecule. And this is actually where our most intense primary bands of our dopant occurs, the CTA molecule. And we can look at how those positions shift when it's incorporated into this new environment. So CTA, when incorporated into the host lattice of TNT, actually shifts from roughly 1 to 3 wave numbers because we have this molecule interacting in its new host environment. And we can confirm by moving to a series of other hosts that we see stretching shifts from 1 to 6 wave number occurring, again indicative that molecular doping is occurring. However, because we collected this IR data at a spectral resolution of 4 wave numbers, we had a reviewer concerned that we could actually not interpret these shifts as significant because they quoted that the error in this position was on the order of 2 to 4 wave numbers. Now, the issue with this is that the reviewer is conflating wave number accuracy with spectral resolution or perhaps even data spacing in your measurement. And when we looked in the literature to refute this claim, we actually saw this is not well addressed in the literature. And in fact, we only found 3 total references discussing error contributions in IR measurements. One was the United States Pharmacopoeia presented a monograph that stated, depending on the particular instrument you used, that you could have positional error as large as 10 wave numbers in your measurement. And then there were also 2 textbooks that stated that your wave number accuracy is equal to plus or minus half your spectral resolution, which is likely what the reviewer was looking at. But we know from our experience of sampling thousands and thousands of spectra, this is not true. So we wanted to come up with an experimental way to demonstrate this. And we also noticed that accuracy and precision were also conflated a lot in the literature. And we took the time to define what those terms meant for this experiment. So accuracy tells you how close your test result is to a true reference value. So you need a standard to talk about accuracy. And then precision is going to tell us the degree of agreement upon our results if we look at reproducing this among things like various instruments, like the monograph is speaking to. So we approached this experimentally to discuss how resolution affects accuracy and precision. And specifically, we wanted to analyze 2 molecules. First was polystyrene. So this is frequently used as the calibration standard in FTIR. And it also comes with NIST traceability. So this is this reference value that we need in order to target accuracy discussions. And it also possesses a wide variety of bands with various intensities, shapes, and broadness that we can also use to discuss other sources of error in our measurement. And then we also analyzed a second molecule, acetaminophen, which is commonly used in the pharmaceutical industry. And this also possesses an IR region that's commonly used to determine what polymorph is forming. So we can first look at peak position accuracy in order to get an idea of what the error in our measurement is. And this is done looking at this NIST traceability document that specifically outlines we are to analyze 9 very specific peaks at a spectral resolution of 4 wave numbers. And I have here the data plotted for the NIST value, as well as our Agilent Nicolau system, as well as 3 of the main manufacturers that we also wanted to analyze in order to see what the instrument contribution of error was. And if we take the peak position values of our instruments and subtract those from what the NIST true reference value is, we get a sense of what the error in our measurement is. So we know that for our Nicolau system, we see that the largest error occurring is roughly 0.1 wave numbers. And even if we factor in instrument variation from other leading manufacturers, we can still see that we can know our peak position accurately within 0.6 wave numbers for a spectral resolution setting of 4 wave numbers. So again, this demonstrates that your wave number accuracy is not directly tied to your spectral resolution setting. We also, though, wanted to be able to evaluate peak positions for molecules that do not come with this NIST traceability, like acetaminophen, but also address accuracy as a function of spectral resolution. So we created this delta term, where essentially we're setting the peak position at the highest resolution analyzed, which was generally 0.5 wave numbers, as this reference value, and then seeing how our position changes by subtracting that from the value known at half a wave number. And we can first demonstrate this with polystyrene on our Nicolau system to show that, again, we have error on the same magnitude of those accuracy values that I presented. And this error is, again, not directly correlated to the spectral resolution setting. So even when we're collecting at a spectral resolution of 32 wave numbers, the largest error we're seeing in our peak position is 9 wave numbers. And at a spectral resolution setting of 4, this is on the order of half a wave number. We also wanted to present, though, something that's more representative of the average error or standard deviation. So we also looked at the average absolute values of these delta terms, which for a spectral resolution of 4 takes that value down to roughly 0.2 wave numbers. We also did the same type of analysis with our other 3 manufacturers, and then we also wanted to analyze this both in our MathScareLab native software that we're most familiar with, which is the Omnic Nicolau system, but then we also did the same processing and analysis in each instrument's native software in case they have factored in any additional processing techniques to account for error that we're not thinking of. And then again, extended this same workflow to acetaminophen in order to make sure that the error estimates we're giving are representative of a larger class of molecules. And what we found is that instrument variation actually has very minor effects on the accuracy in your measurement. And I have here the data represented with polystyrene, but we can see even among the 4 spectrometers, we have a difference in error of roughly 1 wave number. And again, even collecting at low spectral resolutions like 32 wave numbers, we can still know our peak position within 4 wave numbers. And you might think that moving to the high resolution regimes also affords you less error in your measurement. But even at 4 wave number or higher spectral resolution, we can still know our peak position within half a wave number. So we gave the recommendation that if we want to balance both peak error and efficiency, collecting at a spectral resolution of 4 wave number is more than sufficient. And we can also plot our findings alongside what the previous recommendations were to see just how drastically we have reduced the error in our measurement. And this is important for allowing us to interpret more significantly shifts in our vibrational spectra to inform different solid forms. although instrument variation was not found to be one of the main contributors to error, we did find that things like water vapor or noise interference in your spectra did lead to significant error, as well as if you're looking at peaks that are close to nearly saturated, that's also more influential than the actual instrument itself. But even when we account for the largest error incorporating all of these variables at a spectral resolution of 4 wave numbers, we can still know our peak within 1.1 wave numbers. And looking at the average error in our measurement, this is more on the order of half a wave number. Now, if we shift to a complementary technique like Raman spectroscopy, we can also interpret our shifts to roughly the same scale, so I will not go through that data analysis again. But for Raman, what is a challenging aspect is actually selecting your excitation wavelength in order to conduct your measurement. And there does not exist current literature that actually surveys and discusses all of the modern available wavelengths that we can use for this technique. And there are guiding principles that you can use to select wavelengths, like scattering efficiency, which generally suggests employing shorter wavelengths will give you higher intensity. But then also, the fluorescence recommendation is to utilize longer wavelength lasers, like a 785. So again, these do not converge to one single recommendation. So again, we wanted to approach this experimentally, and we surveyed a broad variety of materials that we found commonly subjected to Raman spectroscopy. And one of the first things that we confirmed was that depending on the laser source that you selected, this does not influence the overall spectra in regards to peak position. So position is wavelength invariant, with the exception of graphitic carbon materials. But your excitation source can influence additional data in your background that does significantly contribute to how you can actually interpret your Raman spectra. One of this being the competing fluorescence signal. And this can change the signal to noise available for you for your analysis. And this example with polyethylene terephthalate is actually a prime example of how moving to 785 nanometer laser doesn't necessarily reduce all of the fluorescence in your measurement. And fluorescence can be to such an extreme, like with 405, that we've almost limited any usable signal in our measurement. Excitation source also influences detector sensitivity. So based on the common CCD detectors, we have a reduced sensitivity at longer wavelengths. So if we look at this specific example of high-density polyethylene, we would expect that usually the difference in signal to noise between a 532 and 785 nanometer laser would only be roughly 5 times increase for 532. But the signal to noise presented here is actually at minimum 56 times improvement, and that is due to the reduced sensitivity of this detector in this specific region. And there are also additional metrics beyond just the wavelength itself that can also influence your Raman spectra. So one of those being your substrate choice. So here I have demonstrated a Raman spectra of naflumic acid, where we can see that we actually sample some of the glass substrate itself, incorporating in additional fluorescence that minimizes our signal to noise in that region, which is often why we employ a type of reflective substrate like a steel substrate in order to minimize that fluorescence. We can also look at how the sample itself affects Raman spectra. So analyzing specific single crystals of azithromycin, and depending on how they are oriented relative to your laser polarization, we can get drastically different alterations in intensities and intensity to the scale that actually looks like it introduces a new peak that we can have difficulty analyzing and comparing across multiple spectra. So one way to circumvent this orientation effect is actually powdering your sample in order to minimize these orientation fluctuations. Okay, so overall, I hope I have demonstrated to you that spectral resolution does not equate the error in your measurement for IR spectroscopy. And we've reduced the error in that measurement by an order of magnitude when discussing instrument variation. But 3 other common factors overlooked in the literature was how water vapor or noise interference can also influence your measurement, as well as peak saturation. And then for Raman spectroscopy, Selecting a proper excitation source is really one of the most important features because it can influence competing factors like signal to noise as a result of either fluorescence interference or detector sensitivity. And then I didn't have enough time to go into too much about the band position, but again, minimal contributions to that unless you're working with graphitic materials. Okay, so I'd like to thank Professor Matzker first for his support in this project, my funding sources, and I'd like to thank all of you for listening today, and I'd be happy to take any questions.
Okay, questions?
Hi. So, thank you for the talk. Why does the graphitic carbon give you this inaccuracy with the in terms of bandwidth on Raman?
Mm-hmm. So some of the graphitic materials we looked at, like activated carbon or graphene, these have Raman bands that are known as dispersive modes that actually have specific band enhancements for given wavelengths. So you can get peak broadening and additional peaks near the same area that looks like a shift is occurring. And this can be pretty significant. We saw, I think, up to 60 wave numbers.
Okay. I'm curious how the reviewer responded after you did all this work to address the comment. And to just add on to that, so I'm from industry, and I'm glad to see that you have already identified most of the potential pitfalls. We actually included all those pitfalls in our internal training. Good job.
Thank you. Yeah, reviewer too, he really held on to his argument. We almost got an entire second paper done and submitted before giving in, but this hasn't been a paper that I think is starting to get cited and referenced a lot more.
I had one quick question, actually, to finish things up. So the NIST standards you guys used, the polymer standard, I think, initially for the study that you showed, where did those numbers come from? Are they measurements? How do you know that they're ground truth in the context of these measurements? And do they come with some sort of precision estimate from NIST if there are measurements?
Yes. So these values that I reported for NIST actually came in a document, stated that they were known. I don't think they have an associated error with them specifically, but saying that you should get this value when you analyze the same thickness material.
Oh, one more question?
Yes, just maybe it's a very stupid question. Why the IR, vibration respect the peaks are so broad? Is it fundamental, like intrinsic to the vibrational like spectroscopy, or is it because all the vibration modes are chaotic, like mix of all different vibration mixed together?
Yes, normally when we saw a broader peak, if you did move to higher and higher spectral resolutions, this was more indicative of overlapping peaks, so kind of like you alluded to, different vibrational motions overlapping in one area.
Okay, so if it's very simple molecule with a one bond, the one vibration mode, then you can get like mass spectrometry kind of a sharp peak, like theoretically. Is it possible?
Usually in IR, we have multiple peaks because unless it's just one specific functional group, you're going to have various stretchings, you might have scissoring or bendings, and all of those motions are a little bit different and will show up as different bands in your IR spectra.
I'm just curious, if that is because the peak broadening is caused by all the different, the overlap, vibration mode, then what if you freeze the molecules, the samples like absolute zero temperature, something like that, then you can get a really good structural. Cold
IR sampling is a very common technique, and it's a way that we can get thinner and more intense bands. And it's something that our lab is looking at doing. As I mentioned with our doping system, the second molecule that we inserted was actually at 1% overall concentration or lower. So the sharper we can get these peaks and bands, the essentially more analysis we can do in actually seeing these peak contributions.
Okay, let's thank Shelby again.